National electrical code limits are approached or exceeded when cascading power strips. Let's consider overcurrent protection. National Electrical Code 210.19 states that branch circuits supplying receptacles shall have overcurrent protection rated at not more than 20 amperes. If a 15 amp circuit breaker on the first power strip is used, it may not provide adequate overcurrent protection for the total connected load. Now let's look at circuit loading. National Electrical Code 210.19 states that the total load on a branch circuit shall not exceed 80% of the rated current of the circuit breaker. If the total connected load is less than 80% of 15 amps, it is still possible that a neutral overload could occur due to the high number of devices. And consider grounding. National Electrical Code 250.146 says that grounding metal raceways, enclosures, and equipment shall be accomplished in accordance with 250.130 through 250.136. The grounding conductor in the power strip may not be able to handle the increased number of devices. In practical applications, while the total load may be less than 80% of the circuit breaker rating, the high number of devices can create other issues. Firstly, there's neutral overload. The neutral conductor may carry more current than the circuit breaker rating, causing overheating and potential fire hazards. Secondly, voltage drop can become excessive. The voltage drop across the power strips can become excessive, resulting in inadequate power to the devices. Thirdly, grounding issues can arise. The grounding conductor may not be able to dissipate fault current effectively, increasing the risk of electrical shock. Reference National Electrical Code 2020, specifically Chapter 210, Branch Circuits, and Verse 210.19a. Let's delve deeper into National Electrical Code 210.19a concerning overcurrent protection for branch circuits supplying receptacles. This section is crucial for ensuring electrical safety when dealing with multiple devices connected to a single circuit, such as through power strips. The code mandates that these branch circuits must have overcurrent protection, like a circuit breaker, rated at no more than 20 amps. The purpose is to prevent the circuit from being overloaded, which could lead to overheating, insulation damage, and potentially fires. When cascading power strips, as described, the cumulative load of numerous small devices can still pose a risk, even if each individual device draws very little current. A 15 amp circuit breaker protecting the initial power strip might seem sufficient, but it's essential to consider the aggregate current draw of all connected devices across all the power strips. If the total current exceeds 15 amps, or even approaches that level consistently, the circuit breaker may not trip quickly enough to prevent damage, especially with sustained overloads. Furthermore, the internal wiring and components of the power strips themselves are designed for a specific maximum current. Exceeding this limit, even if the main circuit breaker doesn't trip, can cause the power strips to overheat and fail, posing a fire hazard. Moving on to National Electrical Code 210.19a3, which addresses circuit loading and the 80% rule. This rule is a cornerstone of electrical safety and aims to prevent continuous overloads on branch circuits. It stipulates that the total load on a branch circuit should not exceed 80% of the rated current of the circuit breaker. For a 15 amp circuit, this translates to a maximum continuous load of 12 amps. 15 amps x 0.8 equals 12 amps. The reasoning behind this rule is to provide a safety margin, accounting for factors such as variations in current draw, ambient temperature, and the age and condition of the wiring. Even if the total connected load across all the power strips is less than 12 amps, a neutral overload can still occur, particularly with electronic devices that draw nonlinear currents. These nonlinear loads, common in modern electronic devices like chargers and adapters, generate harmonic currents that flow in the neutral conductor. Harmonic currents are multiples of the fundamental frequency of the alternating current power supply, which is typically 60 Hz in the United States. These harmonics can add up in the neutral conductor, leading to a higher current than what's present in the phase conductors. This is especially problematic in multi-wire branch circuits, where multiple circuits share a common neutral conductor. The neutral conductor can become overloaded even if the individual circuits are not overloaded, potentially leading to overheating and fire hazards. To mitigate this risk, it's crucial to carefully calculate the total load in the circuit, taking into account the potential for harmonic currents. Using power strips with built-in surge protection can also help to reduce harmonic distortion. National Electrical Code 250.146D focuses on grounding requirements for metal raceways, enclosures, and equipment. Grounding is a critical safety measure that provides a low impedance path for fault current to flow back to the source, allowing the circuit breaker to trip and to energize the circuit in the event of a ground fault. A ground fault occurs when a live conductor comes into contact with a grounded metal part, such as the chassis of an appliance or the enclosure of a power strip. Without proper grounding, the fault current could flow through a person who touches the faulty equipment, resulting in an electrical shock. National Electrical Code 250.130 through 250.136 provide detailed requirements for grounding different types of electrical systems and equipment. These sections cover topics such as the size and type of grounding conductors, the methods of connecting grounding conductors to equipment, and the requirements for grounding electrodes. In the context of cascading power strips, the grounding conductor within each power strip must be adequately sized to handle the potential fault current from all the connected devices. If the grounding conductor is too small, it may not be able to dissipate the fault current effectively, increasing the risk of electrical shock. Additionally, the connections between the grounding conductors of the power strips and the main grounding system must be secure and reliable. Loose or corroded connections can increase the impedance of the grounding path, reducing its effectiveness. It's also important to ensure that the power strips are properly listed and labeled by a recognized testing laboratory such as UL or ETL. These listings indicate that the power strips have been tested and meet safety standards, including requirements for grounding. Now, let's address other potential issues that can arise when using a high number of devices connected to power strips, even if the total load is less than 80% of the circuit breaker rating. Firstly, consider neutral overload, which we touched on earlier. Neutral overload is a significant concern in circuits with nonlinear loads, such as electronic devices. These devices draw current in short, sharp pulses, which creates harmonic currents that flow in the neutral conductor. The neutral conductor is the return path for current in a single-phase alternating current circuit. In a balanced circuit, the current in the neutral conductor is ideally zero. However, with nonlinear loads, the harmonic currents can add up in the neutral conductor, resulting in a higher current than what's present in the phase conductors. This can overload the neutral conductor, causing it to overheat and potentially start a fire. It's important to note that the circuit breaker only protects the phase conductors, not the neutral conductor. Therefore, a neutral overload can occur even if the circuit breaker doesn't trip. To mitigate the risk of neutral overload, it's recommended to use power strips with built-in surge protection and harmonic filtering. These features can help to reduce the amount of harmonic current generated by the connected devices. Secondly, let's examine voltage drop. Voltage drop refers to the reduction in voltage that occurs along a conductor due to its resistance. All conductors have some amount of resistance, which impedes the flow of current. As current flows through a conductor, some of the electrical energy is converted into heat, resulting in a voltage drop. The amount of voltage drop depends on the length of the conductor, its cross-sectional area, and the amount of current flowing through it. Excessive voltage drop can cause several problems, including dimming lights, malfunctioning equipment, and reduced efficiency. In the context of cascading power strips, the voltage drop across each power strip can add up, resulting in a significant voltage drop at the end of the chain. This can cause the devices connected to the last power strip to receive inadequate power, leading to performance issues or even damage. To minimize voltage drop, it's important to use power strips with heavy gauge wiring and to keep the total length of the power strip chain as short as possible. It's also recommended to use power strips with surge protection, as these devices can help to stabilize the voltage and reduce voltage drop. Thirdly, let's discuss grounding issues. Grounding is a critical safety measure that provides a low impedance path for fault current to flow back to the source, allowing the circuit breaker to trip and to energize the circuit in the event of a ground fault. A ground fault occurs when a live conductor comes into contact with a grounded metal part, such as the chassis of an appliance or the enclosure of a power strip. Without proper grounding, the fault current could flow through a person who touches the faulty equipment, resulting in an electrical shock. In the context of cascading power strips, the grounding conductor within each power strip must be adequately sized to handle the potential fault current from all the connected devices. If the grounding conductor is too small, it may not be able to dissipate the fault current effectively, increasing the risk of electrical shock. Additionally, the connections between the grounding conductors of the power strips and the main grounding system must be secure and reliable. Loose or corroded connections can increase the impedance of the grounding path, reducing its effectiveness. It's also important to ensure that the power strips are properly listed and labeled by a recognized testing laboratory, such as UL or ETL. These listings indicate that the power strips have been tested and meet safety standards, including requirements for grounding. In summary, when cascading power strips with numerous small loads, it's essential to consider National Electrical Code requirements for overcurrent protection, circuit loading, and grounding. Even if the total load is less than 80% of the circuit breaker rating, other issues such as neutral overload, voltage drop, and grounding problems can arise. By carefully calculating the total load, using power strips with appropriate features, and ensuring proper grounding, you can minimize the risk of electrical hazards and ensure safe power distribution. Let's now explore specific scenarios and calculations to illustrate the practical application of these National Electrical Code principles. Suppose we have 6 power strips, each applying 6 identical power strips, and so on, resulting in a total of 216 individual load connection points. Let's assume each device connected to these power strips draws a very small current, say 0.5 amps. The total current draw would be 216 devices multiplied by 0.5 amps, which equals 10.8 amps. This is less than 80% of a 15 amp circuit breaker 12 amps, seemingly within the safe limit. However, as we've discussed, this doesn't guarantee safety due to potential neutral overload and voltage drop. To assess the risk of neutral overload, we need to consider the type of devices connected to the power strips. If these devices are primarily electronic devices with switching power supplies, they are likely to generate significant harmonic currents. These harmonic currents can add up in the neutral conductor, potentially exceeding its capacity. The National Electrical Code doesn't provide a specific formula for calculating neutral current in circuits with nonlinear loads. However, it recommends consulting with a qualified electrical engineer to perform a harmonic analysis and determine the appropriate neutral conductor size. As a general guideline, it's often recommended to increase the neutral conductor size by at least 50% in circuits with a high proportion of nonlinear loads. In our example, if the neutral conductor is the same size as the phase conductors, typically 14 American wire gauge for a 15 amp circuit, it may be necessary to upgrade it to 12 American wire gauge or even 10 American wire gauge to handle the potential harmonic currents. To evaluate the voltage drop, we need to consider the length and gauge of the conductors in the power strips and the extension cords used to connect them. The National Electrical Code provides tables that list the voltage drop per amp per foot for different conductor sizes. For example, 14 American wire gauge copper wire has a voltage drop of approximately 3 volts per 100 feet at 10 amps. If the total length of the power strip chain is 50 feet, the voltage drop would be approximately 1.5 volts. This may not seem significant, but it can add up if the devices connected to the power strips are sensitive to voltage variations. To minimize voltage drop, it's recommended to use power strips with heavy gauge wiring and to keep the total length of the power strip chain as short as possible. It's also advisable to use extension cords that are rated for the intended use and to avoid using excessively long extension cords. In addition to these calculations, it's important to consider the overall condition of the electrical system. Older wiring may have deteriorated insulation, which can increase the risk of short circuits and ground faults. It's also important to ensure that the circuit breaker is functioning properly and that it trips quickly in the event of an overload or short circuit. Regular inspections of the electrical system can help to identify potential problems before they become serious hazards. In conclusion, while the total connected load may be less than 80% of the circuit breaker rating, cascading power strips with numerous small loads can still pose significant electrical hazards. It's essential to consider national electrical code requirements for overcurrent protection, circuit loading, and grounding, as well as potential issues such as neutral overload, voltage drop, and the overall condition of the electrical system. Consulting with a qualified electrical engineer can help to ensure that the electrical system is safe and meets all applicable code requirements. Remember, electrical safety is paramount, and it's always better to err on the side of caution when dealing with electrical systems. Proper planning, careful installation, and regular maintenance can help to prevent electrical hazards and protect lives and property.